Hi, I'm Alisha Vira. I'm a PhD student in physics, and I'm working on the Reveal survey under Professor Philip First and Professor Zhigong Zhang. Today, I'll be discussing designing a boron nitride polyethylene composite for shielding neutrons. On the surface of the moon, astronauts are exposed to a harsh radiation environment. Galactic cosmic rays interact with the lunar regolith and produce neutrons, protons, X-rays, and gammas. All are hazardous radiation. Neutrons are particularly difficult to shield. The albedo lunar neutrons span a wide range in energy, so it's difficult to design a shielding composite that is efficient at reducing the radiation exposure at this wide range of energies. For this reason, we focus on designing a composite for shielding albedo neutrons. So how do we shield neutrons? From rad worker training, we know that alpha particles and beta particles are relatively easier to shield as they are blocked by a piece of paper or an aluminum foil. X-rays and gamma rays pass through all of this material and are attenuated by a high Z material such as lead. Neutrons are difficult to shield as they pass through all of these materials, including water. The only way to shield neutrons is to slow neutrons down to thermal energy, which is called moderation. Then once they are slowed down to thermal energy, we can capture the thermal neutrons. So thermal neutrons have a high scattering cross-section with a few elements, such as boron-10, increasing the likelihood of undergoing this capture event. So our question is, what is the most optimal distribution of the thermalization and capture elements within a shielding composite to minimize the radiation exposure? So based on these two processes, we want to pick materials that are efficient at thermalizing and capturing neutrons. For moderation, we use high-density polyethylene simply because it contains a high hydrogen component and therefore has a large elastic scattering cross-sections with neutrons. To capture these neutrons, we use hexagonal boron nitride. Hexagonal boron nitride can be fabricated to only contain boron-10 and therefore has a higher likelihood of undergoing this capture event. So boron-10 interacts with a thermal neutron and produces these lithium and alpha particles. These lithium and alpha particles have a relatively short stopping range and can be stopped within a few microns. So what are we doing here? So we're going to approach this question from a unique perspective. Previously, there's many extensive experimental studies on shielding efficiency of HBN HDP composites. However, there's not a comprehensive study on the optimal internal configuration. The best way to approach this question is to design Monte Carlo simulations to simulate a wide range of composites and see which composite does shield these neutrons the most possible way. So for this, we use a simulation toolkit called JON4, which has a wide range of applications. Within JON, we send on neutrons that are uniform in energy and isotropically incident on our HBN HDP composite. In this diagram, we have neutrons that are shown in green, and these neutrons interact with HDP, shown in white, and HBN, shown in gray. Upon interacting with HBN, they undergo this capture cross-section, producing heavy charged particles, such as alpha and lithium particles, and these can give off prompt gammas, shown in orange. So during the post-processing, we want to separate these into different energy ranges to isolate the physics effect within each range. And so we use these standard neutron binning ranges for our post-processing. So we want to explore a variety of composites to answer these three important questions. Does introducing boron-10 improve our shielding efficiency? If boron-10 improves the shielding efficiency, how do we distribute this? If we know the optimal configuration, can we actually manufacture it? So to answer this question, we explore first a homogeneous blend of HDP and HBN, and this is what we call the blended configuration. We also explore a layering of HDP and pure HBN, and this is what we call the ideal layered structure. We note that it's ideal because it's not actually feasible to make HBN that's on the orders of millimeters thick. So in addition, we study a layering of pure HDP with a HBN-HDP blend. And so we have to blend the HBN with a binder of HDP to actually make this composite. And this is what we call the manufacturable composite. We note that the manufacturable composite is compatible with additive manufacturing techniques, which is a necessary tool for space applications. So what we do is we produce over 20,000 simulations, and that produces around 4 terabytes of data. So we need a way to evaluate all of these shielding composites. So for our figure of merit, we use the effective dose. The effective dose is commonly used in medical physics as it takes into account the radiation type and the damage that it does on a particular organ. So it takes into account all of the human effects. So the effective dose as a function of energy is shown here. So the higher the effective dose, the more damaging it is for humans. For example, heavy ions are very damaging for humans, but they're also relatively easier to stop, as opposed to neutrons are pretty damaging across this entire energy range. So our goal is we use the effective dose as our figure of merit to evaluate this wide range of composites. So from looking at our simulation result, we look at the effective dose ratio, the effective dose out divided by the effective dose in, so we can get a factor of improvement as a function of areal density, which is just proportional to thickness. So we've shown a few different reference lines here, HDP shown in gray, aluminum shown in pink, and lead shown in cream. So the question is, where does our configurations fall on this map? We end up seeing that the blended configuration is better than pure HDP across all of the areal thicknesses explored in this study. Now, what about spatially separating these materials? Do we get an improvement in layering HDP and HBN, or is it better to have a composite material with these elements just all mixed in? So from exploring the manufacturable configuration, we see that improves the effective dose ratio by an additional factor of 3 in comparison to pure HDP and 21 in comparison to aluminum. This is a huge improvement that can drastically lengthen mission durations and significantly reduce the radiation exposure that astronauts are exposed to.
2 minutes.
We know that the manufacturable configuration has this interesting feature where the optimal structure changes from being a tri-layer to a multi-layer structure shown in the transition between blue to orange. Now, we don't know why this occurs, but it's interesting to note that the internal structure does play an important role. So overall, we have answered this question of what is the most optimal way to distribute the thermalization and capture elements within a shielding composite. We've explored a design space that is compatible with additive manufacturing techniques and found that including boron-10 in the composite improves the shielding efficiency. In addition, having a layered composite reduces the radiation exposure more than a blended composite. And so our answer to our original question ends up being a little bit more nuanced and clearly worth exploring. I'd like to thank all the students and professors who made this project possible. In addition, the upcoming Clever funding will use these newly developed capabilities to explore some of the dust grain charging. Thank you.
Great, thank you very much. Any questions online or in the room? Looks like we have one question online from Andrew Jordan that asks, is the blended composite harder to manufacture than the layered composite?
So the blended composite is actually going to be easier to make because, so can I go back? So in this plot, we've shown blended composites that have a weight percentage of less than 20 weight percentage, and that's very feasible for material science to actually manufacture. The blended composite is simply easier to make because you just take your your HB and HTP materials and you blend them together, and then you additively stack this material. The layered composite, you have to create different units and stack the units. So it is better to manufacture the blended composite simply just because it's easier. But if we find that we layer this composite and get this additional improvement of 2 to 3, that can reduce the radiation exposure that astronauts are exposed to.
Excellent. Any questions in the room? No? Okay.